From the MATLAB example, I believe that you have some sort of the idea about the weakness of the global histogram and how we can overcome that thing using the adaptive method. So now we will dig in the details from the theoretical aspect of the adaptive threshold. But before that, we will recap back in terms of the weakness of the global method and how the adaptive method works. So basically for this example, we have the image in which the image was overexposed in this area and then underexposed in this particular region. So for this image, we have the distribution of its histogram. So from this histogram, you can see that we have this is the first peak, we have the second peak, and then the third peak. But however, it's quite hard in order to determine the value. We have one value, two value, three value, and etc. So if we try to solve this problem by using the also threshold method, so also will yield the value of 140. And if you use this threshold to find the foreground image, so this is the result, so in which you are able to get the shape of the objects, and foreground also included some part of the image background. So if we try manually to select different threshold value, so this is the result. It is quite hard to relying on the single threshold values to separate foreground from the background for this particular image, because it's quite hard to relying on a single value when you have a non-uniform illumination condition. So for this problem, since we have various issue with the single threshold value, so how we can overcome this thing? So the answer is by using the adaptive threshold. So this is the result if we try to use the adaptive threshold. So for this image, you can see we have quite distinction of the foreground area of the image with respect to the background. Inside of the foreground image, you will have some hole. So this thing can be overcome later on by using the post-processing method, such as the morphological filters, median filter, and etc. that you will cover up in your next chapter. So this is basically the outcome when you use the adaptive threshold method. So the thing is that how the adaptive threshold works from its theoretical perspective. So in order to answer that thing, so we need to find some idea, or we need to recap the idea of the global threshold. For the global threshold, you are given some image and then you will relying the single threshold value. So for this case, it's 164. So you will use 164 in order to threshold throughout the image. So basically this is the concept of the global threshold. So in contrast, with respect to the adaptive method or the local threshold method will relying on the kernel. So kernel is the simple window in which all the value will be equal to 1. So for instance, if your kernel dimension is 3 times 3, so for this case you will have this type of window size in which all the values in here, everything will be equal to 1s. So you will perform the convolution process by using this kernel, and then later on depends on what type of outcome. So let's say you are interested in terms of the mean, so the outcome of the multiplication with respect to this kernel, you need to divide with respect to 9 in order to determine the mean, and the same thing with the other case. So this is the example of the kernel. The green area is the example of the kernel. So what is the kernel do? So we will calculate the threshold inside the region, the enclosure by this green box. So for this small aperture area, so we calculate the single threshold value, and we will utilize this value in order to threshold this particular image area by using the single pixel value. So let's say for this area you have determined the threshold value of 63. So you pick up the pixel value here, and then if the pixel value is higher than 63, then it's belong to the foreground, or if less than that thing, it will belongs to the background image. So the kernel will be slide through the image, and it will be clearly seen that if you move to the next portion of the area, so you will obtain different value of threshold based on this particular region. So you will use the obtained value to threshold all the areas in the input image. So the process will be repeated up until end of the image, until you find the single outcome of the image. We call this thing as the binary image, in which the foreground will belongs to the foreground value will be equal to 1 and the background will be equal to 0. For the adaptive threshold, mainly there are two main approach. The first method is based on the Chow and Kaneko approach, and then the second thing is based on the local threshold method. Basically, for both methods, the assumption is that when we construct the small image area, the small portion of the area from the whole image. So in this small region, the assumption that the illumination will distribute evenly, in contrast to the whole image. If you rely on the whole image, illumination was actually distributed unevenly. But if you take just a small portion of this area, so there's tendency that this small portion area illumination will distribute it evenly. So this is the basic idea of the adaptive method. So for the Chow and Kaneko method, Chow and Kaneko relying on the combination of the OTSU method in the small patch area. So what is the Chow and Kaneko do? So it will find based on the small area region here. So next we construct the histogram, and then from the histogram, by using the OTSU, we will find the single threshold value. So this threshold value will be used in order to threshold the area of image here. So this is basically the Chow and Kaneko approach. However, there is some bottlenecks by using that method. Is that this method is quite slow, because it's quite complicated to calculate the histogram and also for every small patch area. So because of that, it's not suitable for the real-time application. So for that particular reason, in our chapter, we will most relying on the local thresholding method, which is quite simple idea, but the outcome is quite good, quite tangible in order to determine the proper binary image. So for the adaptive threshold or the local thresholding method, so the selection of the value of threshold will use the same concept in which we introduce the kernel. So for every area surrounded by the kernel, we will calculate either the mean of the whole region, the median of the whole region, the mean of the whole region, or the max plus mean for the whole region. So this is actually the average from max plus mean for the whole region. So basically it's quite simple. You just need to construct the small patch area. You need to determine what is the suitable dimension of your kernel, and then later on, instead of the kernel, you need to calculate either median, mean, or max plus mean. So depending on the condition, sometimes it will work based on the mean only, sometimes it only works based on the median, and etc. One thing that you need to remember that when selecting the dimension, you need to select the kernel dimension that is quite large, that able to include between the foreground and the you able to include the area that corresponding to the foreground and background in that particular small patch of the image. So this is important because of you want to find the distinction point, they're able to separate the foreground and the background well. So however, you need to control the trade-off between the dimension of the patch, because of if you select quite large of the area, so let's say you select this portion of the image, so you can see that the illumination of this big patch is non-uniform. In contrast, where you select the small portion of the area, so you really need to control the trade-off when designing the proper kernel dimension. The adaptive method is the less intensive in terms of the computational, so it's quite good for implementation in real time. In our coursework, mostly we will be relying on the mean in order to threshold the image. However, in real application, you can use either the median, the max plus min, and etc. Depending on the condition, as I highlight previously. So if we are relying on the means, for instance, for this case, we have the 7 times 7 in terms of the kernel. So we construct the kernel inside of the image, and then later on we find the threshold. We repeat the same process throughout the image. So this is the result. If we're relying on the mean to find the threshold value inside of the patch enclosure, and then use that value to threshold a small patch of the area to determine the binary image. So based on this output image, what you can see is that we're able to actually find the distinction point. We're able to separate the foreground with respect to the background, even though it's not really proper in terms of the background image. So however, one of the biggest issue for relying on the mean means that in the boundary or in most of the background area, you will see there will be a lot of the salt and pepper noise or small patch of the noise, which is the bottleneck of our binary image. So in order to solve this problem, there is some improvement of the mean threshold selection for the adaptive method. So the method is called as mean minus C. So in this case, this is the combination of the adaptive and global, in which mean was calculated in very small region of the image, and then C is the constant value that we use the same value throughout the image. So there is the global and the adaptive method. So for instance, if you use the 7 times 7 of the image dimension, which is equal to 7, so this is the result of the output when we use this particular concept. In contrast with the previous image here, so you see, if you relying on the mean, so the foreground and background quite separated well, but the background is highly contaminated with noise. So in contrast, if you use the mean minus C, you will have very nice background, and then at the same time you're able to highlight most of the area that belongs to the foreground. So if we use a different type of dimension with different C, so this is the result. So you can see from here, if you use the higher dimension, or you use the larger dimension of the kernel. So you're able to highlight the foreground and the background, but it seems like the foreground text was actually bold. In contrast, if you're relying on the quite small dimension, so this is some trade-off when design the things that utilize the adaptive threshold. You need to properly select the dimension of the image properly. So my suggestion is that you start with the small kernel dimension, and then if the outcome is not satisfied, so you can increase that thing time by time until you get the proper binary image. If we try to use the different type of kernel, previously we used the mean, so let's say we use the median in order to solve the same thing. So this is the result in which even though you're able to separate the foreground and the background well, but the text of the foreground was actually contaminated with some black noise. So as a result, you're unable to read the text properly. So in contrast, if you use the mean, in which you're able to read some of the text quite easily. So this is the result if you use the 7 times 7 dimension when c equal to 4. This is the case of the median minus c outcome. So in a simple way, we can conclude the step of using the adaptive threshold by using this step. The first one, you need to find the convolution of the image, either using mean, median, or whatever, mean plus max over 2. Second thing, you need to subtract the original image from the convolve image. The third thing, you threshold the things by using the C, which is the constant value. This is the global threshold method. And then finally, you invert the thresholded image. So how the step was actually summarized, the concept is based on the simple notation. So basically, in the previous mean minus C, what you do is that you have the original image. So you threshold the original image. So this is if you want to find the foreground. Original image will be higher than mean minus C in order to obtain the threshold. Sorry, in order to obtain the foreground area from this image. So if you do some simple mathematics substitution, so you can obtain mean minus original will be actually less than C. So this is the first step. You find the mean, median, and etc. Second thing is that the second step, you subtract the original from the mean. So in this case, you will use this formula, and then you will threshold that thing with respect to C. So in this case, you will find any information that is lower than C. So this is actually you find the background instead of the foreground. So there is one reason later on you need to invert the threshold image in order to determine the foreground area from the image. So basically, you can just memorize this step, just for a simple step, convolve the thing. Second, the convolve image minus the original. The third step is the find the threshold. So this is where you find the thing with respect to C, the global threshold value. And then finally, you invert the thresholded image. So to make the things much more better to understand, so we'll use this simple example to calculate what is the binary image from this 4 times 4 input image when you use the adaptive method. So for this case, we will use the min minus c adaptive threshold with the 3 by 3 dimension of kernel with c equal to 30. So for this case, for the kernel will be something like this, in which everything here will be 1 1 1 1 1 1 1 1 1, and then the outcome will be 1 over 9 times the kernel. So however, for this example, since we are not considering any padding to this image, so what we'll do, if the kernel is 3 by 3 and then your input image, when you overlay that things only contains 4, so we will divide that thing just over 4 in order to determine a general average for this particular case. So now for this image, so let's say we define the kernel 3 by 3, so this is the kernel of 3 by 3. So for this particular region, the average or the mean will actually 63 plus 63 plus 63 plus 190 over 4. So for this case, you will determine the output of 95. So the next part, we slide the kernel to the next area. So the same thing, 63 plus 63 plus 63 plus 63 plus 190 plus 190 over, in this case, 1 2 3 4 5 6 over 6, you will obtain 105. So we move to the next part, you have 127, and then the final part you have 127. So the process will be repeated for the second column, so that finally you will obtain this combo image. As a result, you do the convolution process from this original image with the 3 by 3 min kernel. So once you find the convolution, this is the first step. The second one is the convolve image minus the original. So you will have the convolve image. So this is the image that we obtain from here. We'll actually subtract with the original image here. So it's just a simple operation of subtraction. So 95 minus 63, you have 32, and then the same process, just straightaway subtraction process. So until you get the whole image, the whole subtracted image. So in this case, because we don't have any mod, so you will have either the positive or the negative value. So the next step is threshold the difference. So you have this image, so you need to threshold the whole image here by using the threshold value c equal to 30. So we have here c equal to 30. So whatever higher density will belongs to the foreground, which you label as 1. Whatever less than 30, you will label as 0, which is belong to the background. So it's quite straightforward. So for this case, this is 1 1 1 1 1 0 0 0 1 0 0 0 1 0 0 0. So you have the outcome here. So finally, invert the threshold that image. So it's very straightforward. Whatever 1 will become 0 and whatever 0 will become 1. So finally you will have this image. So for this case, the shaded area will belongs to the foreground, and then the white area will belongs to the background. So that is actually the step how we are able to calculate the outcome or the output of the binary image when your input image consists of the your input image has the non-uniform illumination distribution. So if I show you a bit in terms of the code in the MATLAB. So basically we will use the same process. So for this case, first we will convolve the image by using the average kernel. So later on we select the value of C. So the first step is this is the second step. You convolve the convolve image will be minus the original image. So next we find the threshold with respect to the value of C. We select the C for this case. So C equal to 0.02. So in general you need to multiply with 255 to determine the original pixel value. So the next in complement means that you just inverse the process. So this is some outcome if we solve problem in terms of the case number 4, and then this is the outcome if you try to solve in terms of case number 3. So that's all.